In this paper, we present a novel approach to infer robot program parameters by inversion of differentiable shadow programs. Consider a skill-based robot program to place an electronics component onto a PCB using force-controlled contact and surge motions. Finding the optimal skill parameters such as velocities by hand is difficult and involves a lot of trial and error. We propose an approach to automatically infer optimal program parameters using differentiable programming. For a given robot program composed of skills, which don't have to be differentiable, we propose to learn a differentiable analog called shadow program, which is trained to predict the trajectory of tool poses and wrenches given a set of program parameters. Instead of learning the shadow program end-to-end, we learn a differentiable shadow model for each skill in the program, which makes the learning problem manageable and allows to reuse shadow models across programs. Shadow models are trained exclusively via unsupervised learning. Because the shadow program is differentiable, program parameters can be inferred by a first-order optimization method for a given set of task objectives. In the first experiment, we show that shadow program inversion can bootstrap program parameters for complex task objectives, like reproducing a human demonstration. We collect 4 demonstrations of a pick-and-place task in virtual reality and provide an unparameterized program skeleton containing a total of 7 motion and gripper skills. Parameters were optimized to minimize a distance function between the demonstrated and expected trajectories. The resulting parameterization solves the task on the real robot. Particularly, the dynamics of the motions could be correctly inferred for all 4 demonstrations. We also consider an industrial use case of placing sensitive components onto a PCB. The task objective consisted of minimizing cycle time while guaranteeing contact with a specific force. We pre-train a shadow model for a linear contact skill from an industrial skill library in a simulation and fine-tune on 500 real-world executions. For each goal force, our optimizer converges at a globally optimal velocity and acceleration. When executing the newly parameterized motion on the robot, the measured forces peak at the desired goal force. In a variant of the same experiment on a different robot, shadow program inversion was used to infer optimal parameters for dynamic movement primitives and UR script functions. Contact forces ranging from 1 to 20 newtons could be reliably produced on a diverse set of contact materials. We lastly consider a task of inserting components into holes on a PCB where the position of the holes is subject to process noise. The robot program consists of an approach motion followed by a spiral search motion. We pre-train shadow models on simulated training data and fine-tune on sampled real-world examples. When inferring program parameters, here to minimize both cycle time and failure rate, the resulting spiral quickly converges to match the noise distribution of the holes. We optimize for different objective functions to demonstrate the capability of shadow program inversion to zero-shot generalize across objectives. When minimizing failure rate, the inferred parameterization results in a large and slow spiral covering the complete noise distribution. When instead minimizing cycle time, the optimizer adopts a fail-fast strategy and trades accuracy for speed. We compare our approach to a baseline programmed by a human expert. When minimizing failure rate, the inferred parameterization is much more robust against process noise. When minimizing cycle time, the resulting motions are short and fast.